what I'm going to talk about is work in progress with Bill Coquet, Manitoba, Canada, and Virgilio Pannone from Firenze, Italy. A subtitle could have been, well, a good subtitle is Reconstruction, Pseudosimilarity, and Edge Replacements. I'm going to emphasize edge replacements. Well, after all, if you have two isomorphic graphs on the same vertex set, an isomorphism between them involves replacing edges, taking them off and putting them where there are non-edges. And in reconstruction, for example, we do the opposite. Reconstruction, we say how many of these edge replacements can we force on the graph G without it becoming isomorphic to the graph H. And I will expand more about this, but this is the sort of point of view. This is what I mean with symmetry between interface between symmetry and regularity. Okay, let's start with some definitions. Reconstruction, when I say a card, I mean a vertex treated subgraph, G minus V. The reconstruction conjecture says that if you have the cards of G, you can determine G uniquely up to isomorphism. An equivalent way of stating is that if G and H have the same collection of cards, then they must be isomorphic. Similarly, there is the analogous edge reconstruction conjecture, which involves edge cards instead of cards. And what about pseudosimilarity? In pseudosimilarity, if two cards of G are isomorphic, then U and V are said to be removal similar. If there is an automorphism of G mapping U to V, then U, V are said to be similar. That is, they are in the same orbit under the action of the automorphism group. And of course, if they are similar, they are removal similar. But U and V can be removal similar without being similar. And in this case, we call them pseudosimilar. So U is not similar to V, but G minus U is isomorphic to G minus V. The most well-known example is the Harari-Polymer graph. These two vertices are not similar to each other. There's no automorphism of the graph which maps this into this. But if you remove the vertex V, you will get a graph, and if you remove the vertex, you will get an isomorphic graph. I cannot not mention this remarkable result by Nash Williams, which is derived from Lova's treatment of edge reconstruction using inclusion-exclusion. And it shows to what extent G and H can be made close to each other with edge replacements. Suppose G is not edge reconstructible, that is, there is a graph H, not isomorphic to G, which has the same collection of edge cards. Then any even subset of edges of G can be replaced with non-edges to give a graph still isomorphic to G, and any odd subset of edges of G can be replaced with an equal number of non-edges to give a graph isomorphic to H. So here we see, I mean, we're forcing so many edge replacements, especially between G and H, but it is still an open question, a big open question, whether, in spite of all of this, G and H are actually isomorphic. Reconstruction and graph symmetry. Okay, let's consider this first. I mean, a vertex transitive graph, or in fact, a regular graph, it's an easy exercise to show that they are reconstructible. Elementary exercise for beginning student of graph theory, but I will come back to it. So symmetric graphs are easy to reconstruct. But is this the real measure of the difficulty of reconstructing a class of graphs? Let's consider what is called the reconstruction number of a graph, which is the least number of cards which are required to reconstruct G uniquely. So we don't use all the cards of G. That must be always at least 3. Now, when you go to vertex transitive graphs, they can have a large reconstruction number, as large as around half the total number of cards of G, half the total number of vertices. But if a graph is not symmetric, if a graph is not just asymmetric, but that is asymmetric, I mean a trivial automorphism group, but also has this property that all subgraphs, induced subgraphs on n-3 vertices, where n is the number of vertices of G, are non-isomorphic, well, then one can show that any 3 cards of G are constructed uniquely. Not that there exist 3 cards of G, which are constructed uniquely, but even more, any 3 cards, give me any 3 cards, and G will be reconstructed. This was used by Milvard, Hertesis, Korshunov, Muller, Bolabash. It is also known that most graphs have this property. The best known proof is by the paper Bolabash in Journal of Graph Theory. But anyway, so in this sense, now it seems that it is easier, because you need less cards in general, to reconstruct asymmetric graphs rather than symmetric graphs. So this issue of reconstruction graph symmetry is quite interesting. It depends a bit on the way one looks at it. Okay, let's give some definitions which will lead us to edge replacements. Well, by notation, when I write US, I mean all pairs with a vertex, from a vertex U to any vertex S in S, except U itself if U is in S. These can be edges, these can be non-edges. What is going to happen most of the time, they will be edges and they will be replaced by another U S prime, where S prime are not neighbors of U. But anyway, let's see the definition. Let G be a graph, and let V be any vertex of G. Suppose there is a set of neighbors of U, it could be all the set, but a non-empty set of neighbors of U, and a corresponding set of non-neighbors of U, in such a way that when we remove the edges from U to its neighbors and replace them by edges from U to the non-neighbors, from G, we get the graph H. In that case, we say that the G is deformable at U, there is a deformation at U, which gives H. For short, we often denote this by simply GU. Okay, so what about reconstruction? Well, by definition, if H is not isomorphic to G and is a reconstruction of G, then for every vertex U in G, there is a deformation which gives H. Why? Because G minus U is a card of G, but it is also a card of H, which is not isomorphic to G. Therefore, we can put U back and join it not to all its neighbors to give H, and that is a deformation. Sometimes we talk about deformation with respect to a property. If we have a situation where a set of properties is recognizable, that is, although we might not know whether every reconstruction of G is isomorphic to G, but we can show that every reconstruction of G has the same properties. For example, the most obvious is the degree sequence, degrees in G. Then we can say that there is, if G is not reconstructible, there is a deformation to a graph, which might or might not be isomorphic to G, but which has the same set of properties. Okay. So an immediate corollary is that elementary result which I mentioned earlier, that regular graphs are reconstructible. Why? Because regularity is a recognizable property. In other words, whether or not the construction conjecture is true, whether or not H is isomorphic to G, we know that H must have the same degrees as G, therefore it is also regular. But there is no deformation of a regular graph, which is still regular. So we cannot deform from G to get a different graph H. This point is basically the starting point. For regular deformations cannot happen, maintaining regularity. What if we extend a bit from regularity? We'll see soon. What about pseudosimilarity? here it's a bit less obvious that deformations take place, but again, quite easy to see. Suppose these two vertices are pseudosimilar in G. So there is a phi isomorphism from this to this. Then the neighbors of the missing vertex V cannot be mapped to the neighbors of the missing vertices of U here, because otherwise phi can be extended to an automorphism of G mapping V to U. A picture will make this clearer. These are the neighbors of the missing vertex V. These are the neighbors of the missing vertex U here. We cannot have NU going to NV, as NV going to NU. So it must go to a different set of vertices. This intersection could be empty, but here we must have something which is not empty. So you put back the vertex V, you put back the vertex U, and we get that G is isomorphic to this. And this is just a deformation at U. And notice that in this deformation, V is mapped to U. So therefore, in this deformation, U switches sides. It goes to the orbit it wasn't in initially. It goes to the orbit of V. Of course, V in this deformation can likewise switch orbits. So we can say that when we say that U and V are pseudosimilar, that is equivalent to saying that U and V are not similar in G, but there is a deformation, GU, there is a deformation at U, which gives a graph isomorphic to G, and the isomorphism between G and GU then maps V into U. So V into U then become linked by an isomorphism. Okay, so that could be the definition of pseudosimilarity in terms of deformations. Now, the point about reconstruction is that G and H share all the cards or many cards. Sharing a few cards is not extraordinary. You wouldn't expect necessarily that G and H are morphic. The same thing with pseudosimilarity. A graph having a pair of pseudosimilar vertices is not extraordinary. And in fact, in a strict sense, it can easily explain why it happens. Rolle's theorem of Wurzel and Coquet. What is interesting is, to make this similar to the reconstruction problem, is when a graph G has several pseudosimilar vertices, not just a pair. For example, one way in which it can have several pseudosimilar vertices, and I'm not going to discuss this problem further, it's a difficult problem, is how large can the size of S, subset of V, be relative to N, and is the size of V, such that S, the vertices of S are mutually pseudosimilar. By mutually pseudosimilar, I mean not only that removing any two vertices will give the same cards, but no two vertices in S are in the same orbit. S cannot be all of VG. Why? Because that would make G regular. And a regular graph cannot have pseudosimilarity. Why? Again, the sentence I highlighted earlier, because the deformation of a regular graph is irregular, because there are no deformations of a regular graph, which is again regular. So the same reason as we had that that H, a regular graph, sorry, is reconstructible. Okay, so we are establishing a bit of a link. I was talking about many pseudosimilar vertices. Just to complete the survey, it is possible to have a graph in which every vertex has another vertex to which it is pseudosimilar. It doesn't mean that they are mutually pseudosimilar, because I mean some could be in same orbits. And the construction by Kimball, Schwenk, and Stockmeyer is simply this. Let H be a graphical regular representation of a group of odd order. And let R be a vertex of H, and consider G to be H minus R. Then G has trivial automorphism group, because the automorphism group of H is regular. Therefore, no two vertices in G are similar. Okay, that's point one. But now, let U be in VG. Therefore, in H, there is an automorphism mapping U to R, and that automorphism continues and maps R to V. And V cannot be equal to U because the alpha would have even order, and we are in a group of odd order. But then H minus U minus R is isomorphic to H minus R minus V. Why? Because alpha maps the set of vertices UR to the set of vertices RV. But this means that G remember, is H minus R. G minus U is isomorphic to G minus V. Therefore, U has the pseudosimilar mate V. Because remember, U and V cannot be similar because G has trivial automorphism group. Therefore, every vertex of G has a pseudosimilar mate. Yet, so in one sense, there is this sort of regularity, there's deformation from one vertex to another. But on the other hand, G has trivial automorphism. So there is a gap between these two possibilities. Okay, let's look at another way, and this is what I'm going to sort of concentrate a bit on, another way in which we can have a lot of pseudosimilar vertices. Let's see G be the number of non-isomorphic cards of G. Let OG be the number of orbits of its vertex. The number of orbits is always greater than the number of cards, because if you have the number of orbits less than the number of cards, it means that there are two cards coming from the same vertices in the same orbit, which is not impossible because similar vertices must be removable similar. But this can be larger than this. Well, this would mean that there is at least one card here, which comes from deleting vertices in two different orbits. But then it means that those two vertices are pseudosimilar. So this can happen only if G has pseudosimilar vertices. The previous construction of Kimball-Schwenk and Stockmeyer gave us a graph with 2K orbits, and at most K cards. 2K orbits because all the vertices are in their own orbits. It's a trivial automorphism group, and the cards could be all non-isomorphic in pairs. And so one question is, can we have less than half of the number of orbits? Can the number of cards be less than half the number of orbits? That's one interesting question, which I'm not going to look at. So what am I going to consider? Well, let's look again at the Harari-Palmer graph. It has 6 cards, because these two give me the same cards. U and V give me the same cards. So 1, 2, 3, 4, 5, 6 cards. But these two are in a different orbit, so 6 cards and 7 orbits. So as I said before, the number of orbits is greater than the number of cards, therefore there are pseudosimilar vertices. This is a graph constructed by Anderson, Ding, Sabeduzzi, and Vestergaard. Well, actually, they constructed the graph, whose line graph then is this, but I'll talk a bit about what they did. And here we have 5 cards, 5 because these 4 vertices give us the same card. If we remove them, the graph is isomorphic. So 1, 2, 3, 4, and these 2 again 5, because they're in the same orbit. However, these 2 are in an orbit, these 2 are in the same orbit, but they are in different orbits, therefore they are pseudosimilar. So we have 5 cards, but 6 orbits. So with only 1 card, we cannot have pseudosimilar vertices. Why? Because with only 1 card, as I said, the graph is regular, and regular graphs cannot have pseudosimilar vertices. But what about if the graph has only 2 cards, or only 3 cards, or only 4 cards. Because with 5 cards, we know it can start having pseudo-similar vertices. N, G, B, pseudo-similar. Therefore, there's this gap here. And the problem we are considering is, we call it the TCTO problem, because we conjecture that 2 cards imply 2 orbits. So that 2 cards cannot have pseudo-similar vertices if you have only 2 cards. Now, I must point out this, that Anderson, Ding, Savidusi, and Vestergaard in 1990, the paper appeared in 1992, they showed that they were working with edge cards. They showed that if you have only 2 non-isomorphic edge cards, it does imply that, that there are 2 edge orbits. That is, there are no pseudo-similar edges. But what happens with 3 edge cards and 4 edge cards is also still open. So if we manage to prove this, we'll have this gap both for edge cards and both for vertex cards. Do 3 cards imply not pseudo-similar? Do 4 cards imply not pseudo-similar? I believe somewhere around here, pseudo-similar edges may get 4. Will start to appear, but even that we haven't been able to do it, and even Vestergaard, Savidusi, Ding, and Anderson couldn't find pseudo-similar edges here, but they couldn't show that there aren't any pseudo-similar edges. Okay, let's now concentrate a bit on this. So we would like to prove this conjecture. So we assume that it has only 2 cards, the graph G, and it has pseudo-similar vertices. And we try to get a contradiction. So what properties would a graph G, which has only 2 cards and has pseudo-similar property vertices, what properties should it have? And this is the little we know. I mean, it's little because it's all, as I said, this is an elementary problem to state, and these are all elementary things which are just consideration of simple arithmetic. I'll show you a bit what I mean. The vertices must have degrees d plus 1. The degree classes must be an equitable partition. This is what this is saying. The alphas and the betas are the degrees from one class to the other or within the class. And we have either every vertex of degree D is deformable to give us G. We cannot have just one. As soon as we have one of that degree, we will have all of them. Or similarly, all vertices of degree D plus 1 are deformable, or it could be that both vertices of degree D and vertices of degree D plus 1, all of them are deformable, which is not saying mutually pseudo-similar. What about reconstruction? Because we're also interested in reconstructing graphs with 2 cards. Suppose it is not vertex reconstructible, and the situation is very similar, but a bit stronger than pseudo-similarity. The vertices must have degrees d plus 1. Every vertex of degree D must be incident adjacent to the same number of vertices of degree d plus 1. Therefore, this is saying that the degree classes form an equitable partition. And now every vertex of W, not as we had before, either all the D vertices or all the D plus 1 vertices, or maybe all of them. Now, only this can hold if the graph G is not reconstructible, that every vertex W has a deformation which is isomorphic to H now, not to the same G, to H, if it is not vertex reconstructible. So there is this connection between them. And the problems become, look very similar. Let's strip the problem of the symmetry condition. Let's only consider regularity. So in other words, all that this is saying, suppose the degree classes, here are the D+1 vertices, and here are the vertices with the degree T. Suppose they form an equitable distribution, and let alpha be the degree here, beta the degree from a D vertex to a D+1 vertex, and similarly gamma delta. Okay, we call it constant degree splitting. Maybe found the best name for it. And this, I just use this diagram to remember this technique. Okay. All right. Now, only regularity, we translate those two earlier problems without invoking isomorphism. So let G be of this type. Okay. Suppose that either every D vertex has a deformation GU, and we're not insisting that the deformation is isomorphic to G, but that it is constant degree splitting with the same parameters. Or suppose that every D+1 vertex has a deformation, which not necessarily gives us G, but gives us a graph which is a class is equitable distribution with the same parameters. Or possibly we have the third condition where both D and D+1 vertices are deformable. Okay, we just call them deformable instead of saying deformable to give a graph with the same parameters, etc., etc. In increasing order of difficulty, the problems will be this. Show that G is reconstructible. When G is not reconstructible, then the third condition must hold, as we said. Both vertices of degree and D+1 have to be deformable. And yes, we can prove that. Show that G does not have pseudosimilar vertices. Here, we can have either only the D+1 or only the D vertices, which are deformable. And we're close to it, but we haven't yet got it. And a bit more difficult will be to characterize the class of graphs which have this property or this property. And in fact, I'm going to show you examples of such graphs. How do we go about tackling this? Well, Bill Coquet uses as another way we're investigating, which uses what he calls partial automorphisms, the isomorphism between G minus U and G minus V when U and V are pseudosimilar. He created this concept several years ago, and we're using that also. But here I'm going to present the simplest, just elementary counting. If this is deformable, therefore these edges can be replaced by edges from U to here, and the graph will still have the same parameters, then take a vertex X. R will be how many vertices in here it is adjacent to, and S will be how many vertices here it is adjacent to. X, after the deformation, becomes a vertex of degree D. Therefore, its parameters from gamma delta have to become alpha beta. It has lost these vertices, which are of degree D+1, and these have taken their place. These are now of degree D, and they're replaced by vertices here of degree D+1. When we do that, and we do a bit of arithmetic, we find that R minus S must be constant for any U, for any X. I'm not saying yet that R and S are constant, but R minus S is constant. Why? Because if you put H equals R minus S, then the parameters alpha, beta, gamma, delta are related by this, and the parameters are constant, therefore H is constant. Similarly, if instead of having a D vertex, which is deformable, we have a D+1 vertex, which is deformable, well, then we have something similar, but this time H prime is still R minus S. It's a different R, a different S. Different vertex, different context here. This is deformable. But still H prime, which is R minus S, is constant, and we have a slightly different relationship between the alpha beta gamma delta. So this was the relationship before, and this is the relationship after deformation. Now, why does this give us reconstruction? Because if there is reconstruction, then then this must happen, and this must happen for all d vertices and for all d plus 1 vertices. But in that case, we can show by comparing this to this, so simple arithmetic, we can show that H equals H prime plus 1. But also using the same argument as the previous diagrams, but instead of with a single vertex with some other configurations, we also prove that H equals H prime. This is a contradiction, therefore we cannot have both d vertices and d plus 1 vertices deformable, therefore the graph is reconstructible. What about, therefore, graphs in which only these are deformable, or only these are deformable, only the vertices of degree d or the vertices of degree d plus 1? Do we have examples? Do such graphs exist? Yes. For example, consider the complete bipartite graph S plus 1. These vertices have degree S, and these vertices have degree S plus 1. That's degrees, has parameters, and any vertex here is deformable. You remove its neighbors with these vertices, and you join them with the neighbors which are right now in its bipartition. This S becomes 1 over here, and we still get K S plus 1 comma S. So not only do we get a graph which has the same constant degree splitting with the same parameters, but we get isomorphic graph. Okay, take its complement. You take its complements, we get the other way around now. I mean, these are vertices of the higher degree, these are vertices of the lower degree. And if you take a vertex here and you deform it by removing all its edges in here and joining it to the vertices in here, this flips side, it becomes a vertex, it becomes a vertex of the in KS plus 1, and we get again the same graph. So the complement of this is this. And of course, if we take multiple copies of this, if we take 2 copies of this, we will get still a graph which has all the vertices of the lower degree deformable. Okay, and still is constant degree splitting with the same parameters. So if we take the complement of this, here's this, we'll get a graph in here. Similarly, we can duplicate this graph. Okay, we need not have the same copies of this of KS and the same number of copies of KS plus. We can have 2 of these and 3 of these, for example. Okay, but I've put them here at the entity. You take the complement of this, and if you take the complement of this, you will get the complete bipartite graph KS S and S plus 1, S plus 1, S plus 1. And again, here now we have that every vertex in here, the vertex of lower degree is deformable. Yeah, and you can go on like this and generate graphs of that type in this way. And this leads to a bold conjecture. Why bold? Because we don't have a lot of evidence in its favor, although we are sort of getting there a bit. First, before the conjecture, facts. if you have a graph of this type, now remember this is a graph which is by degrees, the n plus 1, the degree classes form an equitable partition, and it has either all the lower the vertices of lower degree or the vertices of higher degree, all of them deformable. And if you put that graph in a column here, like I started with KS S plus 1, and either duplicate or take complementation and duplicate, take complementation, and so on, you will get a column of graphs in which vertices of lower degree are deformable, and a column of graphs in which the vertices of the higher degree are deformable. But the conjecture is this, that every graph of this type, which has either all vertices of lower or all vertices of higher degree deformable, are in the above table. Therefore, they can be generated starting from KS S plus 1. This is obtainable from this by a sequence of duplication and complementation. Okay, so basically, I'm saying that this contains all these graphs. As I said, we're still calling it a bold conjecture. If we get a bit nearer, we become a conjecture. Okay, this is the conjecture I wanted to get to. Of course, this leaves open also. These are the difficult problems now. Go back a bit. Graphs with 3 cards, can they have pseudosimilar vertices? Graphs with 4 cards, can they have pseudosimilar vertices? These could be difficult problems, but not as hopelessly difficult as finding the largest S set of vertices which are mutually pseudosimilar. That seems really, really difficult, but still it is trying to force a lot of pseudosimilar vertices, but this is more focused. You have 3 cards, you have 4 cards. So these are not easy, but doable. Maybe, I mean, interesting research questions. But now, having presented that and left those 2 problems, I want to show that this idea of replacements, edge replacements, can crop up in very different contexts and still give an algebraic graph theory interest. So the context is this. Okay. Amoebas, type of graph which were invented by Yair Caro, Adriana Hansberg, and Anita Montejano. And they come from a very surprising area. What area? A sort of Ramsey edge coloring problem, which is also close to zero-sum problems. So a graph G, I mean, this is the definition here, but I'll explain it in words. Graph G is said to be balanceable if we take a sufficiently large N, and if we make sure there is a K, that's such that if we make sure that there are at least K edges of any color, this is, in Ramsey, we don't force that, but here, you see why, we force that the number of edges of red or blue has to have at least K. If there is such a K, such that for any 2 coloring of Kn, there is a copy of G with half of its colors in one color, and the copy of G with half of its colors the other color. If the edge number of edges is odd, we take the floor and the ceiling. Then we say that the graph is balanceable. Okay, Caro, Hansberg, and Montejano extended this and said, well, if there is such a K and for N sufficiently large, now what we want is that in every edge coloring of Kn from a certain point onwards, you can find, what this means is you can find a copy of G with all its edges red, and a copy of G with all its edges red except one blue, and a copy of G with all its edges red and except two blue, and so on, up to a copy of G with all its edges blue. In that case, we say that G is omnitonal. Okay, and so balanced omnitonal are, of course, an extension of balanceable balanced graphs. What is this got to do with replacements? Well, first of all, it can be shown using Turan's theorem, that this must be omnitonal graphs must be bipartite. Okay, so Caro Hansberg and Montehano defined amoeba as following. Amoeba is a graph of G, such that if there are two copies of G in a complete graph, then we can go from G from one copy to the other copy by replacing an edge with another edge, and then replacing an edge with another edge in steps like that. Okay, each HI is obtained from HI by means of an edge replacement. Okay, and all of them still isomorphic to G. Okay. That is what they say they call an amoeba. And why is that? Well, because bipartite graph, and it's can tell even intuitively without going to a detailed proof, that a bipartite graph, which is also an amoeba, is omnitonal. Why? Because, I mean, when you start with one which is completely red, and you start moving to one which is completely blue, first that they must exist, but then when you start moving from one to the other, you're changing one edge at a time. Therefore, the color partitioning of the graph has to go through all the partitioning, 0 blue, all red, 1 blue, all the rest red, up to all blue. So there's this omnitonal, this amoeba concept. Let's look a bit at this amoeba concept. This graph is an amoeba. How do Caro, Hansberg, and Montehano prove it? They do this. Just add a single vertex, okay, and do an edge replacement. Well, first of all, look at the graph and consider its automorphism group. There isn't much to consider. In this case, there's only this non-trivial automorphism. But in general, you might have to use the whole automorphism group, which is larger. Then add a single vertex, just one vertex, and do an edge replacement, do the isomorphism, and see what permutation it gives you. And it gives that permutation. Do another edge replacement, consider the isomorphism, which gives you this permutation. Do another edge replacement. This edge has been replaced by this edge. Okay. And it gives this permutation. Now, you consider all permutations of this type together with the automorphism group of the graph. If between them they generate the whole symmetry group of 6 vertices, Y6, because the graph had 5 vertices, 1, 2, 3, 4, 5, and we just added a single vertex. If the graph, those permutations generate S6, therefore G is an amoeba. This is one of their theorems. So we are extending the automorphism group of G in some fashion, and if by doing that we reach this, then G can be moved all over the complete graph to any other G which is isomorphic to it. All this and more is in this paper. Now, in this paper, Caro Hasberg and Montano, they consider amoebas without going into the coloring aspect. So if you're not interested in the coloring problem, but you're interested in amoeba as a concept with an algebraic graph theory, this paper is the paper to go to. There's a lot of results and constructions. It's still in preprint fashion, but I've given the reference here. Before finishing, I want to mention also some other work related to edge replacements. This summer, when I was looking at this problem, I remembered that, oh, by the way, yes, I forgot to say that we extended this definition of amoeba, where instead of going from G to G, we have a family of graphs. And you go from one to the other by a sequence of edge replacements. And these steps, they don't need to be isomorphic to each other, but they have to be isomorphic to the graphs in the closed family, in that family. And when you look at this, you immediately realize that there's one obvious example from matroid theory. The spanning trees of a connected graph K are an example. You can go from one spanning tree to another by replacement of single edges. And at every step, you remain with a spanning tree. So this issue of edge replacements can also be extended and you have contact now with another area of combinatorics and graph theory, with matroid theory. As I was saying, this year, in summer, looking at these problems, I suddenly remember that 30 years ago, well, such a long time ago, certainly before we had internet, I would say, because I used to receive reprints from John Sheehan in hard form. He sent me some preprints, and I suddenly remembered and started looking them up, revisiting them. He gives these definitions. You can notice now how familiar it is to what I've been saying. Graph G is K-free, then a set of K edges can be replaced by non-edges to give a graph isomorphic to G. He was inspired, of course, by Nash Williams' lemma. In fact, he defines even free to be a graph which is K-free for every even K. And by Nash Williams' lemma, if G is not edge reconstructible, it is even free. It's a short way of stating the first condition of Nash Williams' lemma. And I've got a paper of his, I think 1972 is the earliest where he started considering this problem. And then 20 years later, there are other papers in between. There's another paper where he considers two free threes, and I must say that I am understanding this paper a bit better now than I did 30 years ago, because I'm looking at it from the perspective I was talking about today. And finally, three more recent papers. These three papers, they consider what they call swappability, swapping of edges. K swappable is not exactly the same as any set of K edges can be replaced by K non-edges, but it is close, okay? And so there is this concept of swappability, which is a relaxation of the concept of replacement of edges. And these problems, these three papers are recent, and I recommend that anyone who's interested in any of this should also have a look at them. And that's it. Thank you very much. Thank you.
Thank you. Thank you very much for this nice talk and for giving us a review in some sense on all the new results on the reconstruction problem. Thank you very much.
Thank you.
Are there further questions to Joseph?
If I may.
Yeah, sure, Robert,
Yes,
please.
hello, Joseph.
Hello, Robert.
I wasn't aware that you were still working on the problem. So
No, I started recently, looked at it, and I was surprised. I was surprised that we hadn't looked at it years ago.
I'm looking at this problem for 20 years now, and
Yeah.
I'm still hoping to get a paper where I will solve at least one of these questions.
Okay.
But I did.
Good. You're confirming to me that they are not trivial questions, because at first that's what I thought.
No, they're not trivial questions.
Good.
But yeah, I will get something done one day on this. But thank you very much for your talk, because yeah, there were some things that I didn't know that you mentioned.
Yeah.
Thank you.
All right. Yeah.
Thank you very much, Robert. Thank you.
Yeah. Yeah. Any further questions to Joseph?
We will have the
I'm
slides,
just
right?
wondering about this.
Yes.
Oh, excuse me.
Sorry, I was just asking. We will have the slides, right? So.
Oh yeah, sure, of course, yeah.
Okay. So that's all. Sorry for interrupting.
Yes.
Okay, yeah, I just wondering about this surprising paper on graph isomorphism and amoebas. Is it, well, I mean, is there some connections with computer science on this
Which
paper?
one? The one on amoebas?
Yeah, right, yeah.
This one. This one.
Right,
Is
yeah.
No, in the paper, no.
No.
And not, there could be, but haven't thought about it as far as I know. I'm not sure. Talking with, with Caro Hansbang and Montejano, I don't get the impression that they thought about it, but I'm not sure.
Well, I'm just asking about motivation. I mean, maybe the problem
Their motivation was the coloring problem.
from coloring, yeah.
From that flimsy type coloring. Then they realized that amoebas give the omnitonal graphs, and not are examples, bipartite amoebas are examples of omnitonal graphs.
Right, yeah, right.
And then they realized that amoebas have their own interests, and they produced this paper.